In this video, I'm going to explain about the working principles of the DC machines. So the machines in machines, the energy conversion is due to the two principal electromagnetic phenomena. The first one is when that the conductor moves in the magnetic field, the voltage EMF is induced in the rotor conductor. And the second phenomenon is when a current carrying conductor is placed in the magnetic field, the conductor experiences a mechanical force. So generally, all the generators work on the principle of dynamically induced EMF. That is based on the Faraday's law of electromagnetic induction. With this law, so it says that whenever the number of magnetic lines of force, that is flux linking with the conductor or a coil, changes, an electromotive force is set up in that conductor or the coil. So the change in flux associated with the conductor can be achieved when there exists a relative motion between the conductor and the flux. So generally, in order to generate the EMF, we need three key features. Like first one is we need the conductor. Second one is we need the flux, and the third one is relative motion between flux and conductor. So here we can either have flux in a motion or conductor in a motion with respect to each other. For example, if conductor is moving, your flux should be in stationary, or if that if that flux is moving, your conductor should be in the in stationary. So the relative motion can be as I said, the relative motion can be achieved by rotating the conductor with respect to flux, or by rotating the flux with respect to a conductor. The voltage gets generated in the conductor as long as there exists a relative motion between the conductor and the flux. So such an induced EMF due to the physical movement of coil or conductor with respect to flux, or the movement of flux with respect to coil or conductor, is called the dynamically induced EMF. So this is the Faraday's law. But in the practical application, in our generator, only that conductor is rotating and flux is stationary. So conductors are rotated with the help of the prime movers. Now the examples are, we have diesel engines, then steam engines, steam turbines, water turbines, and the wind turbines. So these turbines, diesel, steam, water, or the winds, helps to rotate the conductor, and that rotating conductor cuts the magnetic flux by keeping the flux stationary. The output generated voltage or the EMF induced in the conductor depends on the number of conductors connected together in a specific manner. We have like the types of winding we are going to discuss in the next video. Is connected together in a specific manner to form the winding called the armature winding. Now this armature, we also call it as a rotor in our practical applications, and the part on which the windings are kept is called the armature. And as per the theory, we have to use the magnets to produce the magnetic flux, but in the practical application, in order to produce the good strength of the magnetic flux, we are using the field winding, which we also call it as a excitation. This excitation is the source from the outside part. So the necessary magnetic flux is produced by the current carrying winding called the field winding. Now here you have the figure for the generator. This one is the armature that we're discussing, which we also call it as a rotor. And then if you again further go in detail with that rotor, this part is armature and inside is called the armature slot, and then you will see the windings in the here. So these windings are called the armature winding. And then in the figure at the left is the stator. In the stator also we have the winding, which we call it as a stator winding. And then the function of the stator winding is to produce the magnetic flux, okay, to produce the magnetic flux. And how to produce that one? We are supplying the current from the external source, which we call it as a excitation source. So inside this one, so inside this stator, we have to put this rotor here, and then when this okay, we can also assume that there's a magnetic flux between this, and then when there's rotation in the rotor, so which means that conductors, the armature windings is also moving along with the rotor, so it will move something like that. Then during that time the magnetic flux is being cut by this armature winding. So in that case the EMF is being induced in the windings at the armature side. So EMF is induced in the armature winding. So in that way EMF, whatever that EMF generated is being taken as the output. So now how to collect that induced EMF, again I'm going to discuss in the next video. Now we are using the Fleming's rule to give the direction of the generated EMF. Now Fleming's right hand rule is used for the electric generator, and the Fleming's left hand rule is used for the electric motors. Now Fleming's right hand rule, so if you place our fingers, the thumb, middle finger and the index finger perpendicular to each other, separated by the 90-degree, like x, y, z plane. For example, we have y, x and z plane. So each plane is being separated by the 90-degree. So our our three fingers should also be stretched like that, and then your thumb should be pointing at the direction of the relative motion, and then your index finger in the direction of the magnetic line of force. Then your middle finger will give you the direction of the induced current. So this is Fleming's right hand rule. And now we have the scope to change the direction of the current or the direction of the rotation. Now our main requirement is to change the direction of the induced EMF. So for this one, let's say that in the first two figure, I'm keeping this one as figure 1 and figure 2. In these two figure, the magnetic flux direction is from north to south. They are in same direction, and then the relative motion of the conductor from here for the first figure, okay, is from left to right. So in that case, if you use the Fleming's right hand rule, the EMF induced in this particular arrangement is current is flowing towards the observer. For example, just place the paper and then put your pen on top of this, and then assume that you have current, the flux direction like this, and then rotor direction like this. During that case, if you place the Fleming's right hand rule, then current will be moving towards the observer. And then in case of the second figure, now here the rotor direction is changed, the relative motion of the conductor is from right to left. So in that case, your current direction is moving away from the observer, which means we have the scope to change the direction of the induced EMF, or we also have the scope to change the flux direction. So if you remember the right hand thumb rule, the flux direction can be also changed, and we also have the scope to change the relative motion of the conductor. We have three scope. If you want that current direction in different way, we can either change the direction of the magnetic flux or the rotation of the conductor. Now the magnitude induced is given by E is equal to that the induced EMF E is given by the magnetic flux times the length of the conductor and the velocity of that conductor is moving. So these units are in meter and meter per second. Here we say that is active length. So active length means the conductor which is under the influence of the magnetic field, and then this velocity is the relative velocity component of the conductor in meter per second in the direction perpendicular to the direction of the flux, which means we should remember that if this is the direction of the flux, your V should be perpendicular, which means it should be separated by the 90 degree. Now let's say your velocity is not perpendicular to the flux. So in that case, we can resolve the components of the velocity as shown in figure B here. In the figure B, our induced EMF is given by E is equal to magnetic flux times the active length of the conductor times the components of the velocity here, V sine theta. Now in order to have the maximum induced EMF, as we have discussed, that V and B, that velocity and the flux should be separated 90 degree. So in order to have maximum E, your theta should be 90 degree. And then in order to have the minimum E, if the induced EMF is 0, it will be either that theta is equal to 0. So using this one, so looking at this, now we understood that our generated EMF or induced EMF is in sinusoidal, but we are talking about the DC machine. So we are going to discuss how to convert this sinusoidal into the direct current or the DC EMF by using one device. Here we are using the commutator. So that commutator is to convert the sinusoidal EMF into the DC. Okay. From the equation of the induced EMF, the basic nature of generated EMF is sinusoidal. To produce a DC EMF or the unidirectional EMF, a device called commutator is used. And an alternator without commutator is called the AC generator. The construction principle is same for both DC and the DC generator and DC motor. And there is difference between construction of the DC generator and the AC generator, though their working principle is same. So that difference between AC generator and the DC generator is the usage of the commutator. Okay, commutator you will find it in the DC generator, whereas in case of AC generator we will not see that, because that generated EMF is sinusoidal. If it is sinusoidal, then we call it as a AC, right? But in DC machines, our output requirement is unidirectional. Now the function of the commutator. So I'll talk this one in the next video.